So last chapter was all about getting the basics down and learning about the ideal gas equation. Now we're going to take this a step further and look at thermodynamics. So now we're going to introduce those concepts that pretty much were summarized in chapter 5 in the Brown book, this Chemistry of the Central Science. But it could be in various chapters in the early books. So the first thing we need to think about is the energy of a system, whether this being the potential energy, the kinetic energy, the electrical energy. We're looking at the internal energy of the system. Now, depending on how your book was, you might have seen this as just E, but in this book, we see it as the term U. Not always the most useful energy, the internal energy U, but it is one that will come up quite a bit for a while. We learned in there about the first law of thermodynamics, that this internal energy must be conserved. It can neither be created nor destroyed. It has to be transferred. So any energy that leaves a system must thus go to the surroundings. Every energy that enters a system must have come from the surroundings. We're not getting free energy. So with that in mind, internal energy is an isolated system. No energy or matter transference is possible, but in an isolated, the internal energy of an isolated system must be constant, because if nothing can transfer from the surroundings, no energy can enter. So with that in mind, we can state that internal energy of the system must always be equal and opposite to the internal energy change in the surroundings. The sum of system plus surroundings must equal 0. The delta U system is negative delta U surroundings. So when it comes to generating U, there's lots of different types of energy you can look at. The two most common ones we will look at are having to do with heat and work from the chemical reactions. Heat and work. So Q is heat and W is work. And so we can say that the change in internal energy is equal to the sum of whatever heat is generated and work is generated. Now we're going to discuss these in greater detail in the following slides. Needless to say, we're going to define them in terms of state variables, pressure, volume, and temperature to make our lives a little bit easier. But with that in mind, we can define, well, at least start by defining 3 major situations where we keep one variable constant for simplicity's sake. And we'll deal with these separately. So we can think of an isothermal system. So a reaction or some sort of process where the temperature remains the same. Pressure is allowed to change, volume is allowed to change, temperature stays the same. An isobaric system, where pressure remains constant, while volume, temperature is allowed to change. So if I heat up a balloon and it expands at a constant pressure, isobaric system. So isochoric, a little bit stranger of a name, but constant volume process. So if I put a box that's sealed with rigid walls and I heat it up, the volume of the box is not allowed to change, but the pressure will build up within that box. So think of those 3 systems to start off with, at least. Now work, when we deal with work is defined as a quantity of energy that flows across a system surrounding barrier that we can use to change the height of a mass in the surroundings. It's the easiest one. So I have a little piston in here with a movable wall with a mass on top. At equilibrium, the pressure of the mass down will equal the pressure on the mass of the gas upwards. Work is done by the gas when it pushes and expands and pushes that mass up. Work is done on the gas when the mass pushes down and causes the gas to contract. Simply put, work is defined as a force applied over a distance. So now work only appears during a change in internal energy. So we will not see a delta W. There is no delta W. W in itself is a change. There is no net work. Work is a change within the internal energy. Work will only change in accordance with the first law. The physical observation of work is the change in position of the mass. So, and terminology, if work leaves the system, making work negative, then the mass goes up. If work enters the system, the surroundings, we have positive W, and the mass is going down as it presses on the gas. Now, there's many different types of work. We will mostly just use one type, but we can look at multiple different types, because work is defined as the integral of a force applied over a changing distance. So a force applies over length. So we can most often look at this as a gas pressure. The pressure is, or force is, pressure times area. As we said, pressure is force over area. So pressure times area times a length, thus changing area and changing length means changing volume. The most common one we'll see is work is defined as negative P external pressure times delta V. So negative P delta V. This would give us, as the volume expands, at a constant external pressure of that mass, that we see a negative work. If the gas contracts, as the volume goes down, it would give us a positive work. Now, if we check the units of this, units of work is typically a joule, but a joule is defined as a Newton meter. Newton is a force, meter is a distance. So force times length is a Newton meter. Pressure is a Pascal, but a Pascal is defined as a Newton per meter squared. So Newton per meter squared times volume, which would be meter cubed, would give us a Newton per meter, and thus a joule. So units here need to be Pascals per meter cubed in order for this to work out. Now, that's the most common type of work we'll look at, but we could also look at things like stretching of a spring, where the force is the tension of the spring and the distance that the spring is stretching. You could look at stretching of a surface area of a balloon or bubble. That the area, we're looking at the area, surface area of the bubble changing as we look at these kind of the pressure, external pressure of that bubble. Now, the last type is a little weird. We'll get to it much later. We won't worry about it right now, but it's electrical work, which can be described as a charge applied over a potential. So charge Q times potential phi, where it's easier way to calculate charge is a current applied over time, or current times the voltage times the time, or amp volt per second, or coulombs volts, gives you a joule. So, okay, so quickly, let's try to calculate the work of these various systems. Just the hardest part here is just watching out for the units. Watching out for the units. The units will kick you if you're not. Gas expands from 4 liters to 10 liters under external pressure of 3 bars. So, negative P bars times delta V, so times 6 liters, would give us negative 18 bars per liter. So, what the problem is, liters, there's 1,000 pascals. I think 10,000 pascals in a bar, but there is 100 meters cubed and a liter. Basically, long story short, a bar liter has to be multiplied by a factor of 1,000, factor of 100 to get it into a joule. So this would give us 18 times 100, so negative 1,800 joules. A spring contracts from 3 to 1.5 centimeters, force of 5 newtons. So insert the tension, negative 5, length, 3 to 1.5, so it's negative 1.5 centimeters. But we need to turn this into, this is Newton, so this is good. I need to turn this, so well, there's 100 centimeters in 1 meter, so 0.075 joules. So work is being done on the spring. Not much work, but enough work. Current 3.2 amps passed over a 12 volt resistor for 10 seconds. 3.2 times 12 times 10 amps, volts, seconds. That's work. 3.2 times 10 times 12. So 384 joules of work in that last one. So now the other half of our internal energy is heat. Once again, heat, like temperature, is kind of amorphous. Heat is defined as a quantity of energy that flows across the system, essentially the barrier, due to a temperature difference. So heat only appears as a change in internal energy. So heat is not a set thing you can measure as like the heat of a system. You can measure the temperature of a system, but you cannot measure the heat. Heat is a flow of temperature, a flow of energy as temperature. It's going to fit with the, in accordance with the first law, and we're going to see a change in temperature to be a heat. When we have a high temperature surroundings and low temperature system, heat will flow into the system. So it's cold out, or it's hot outside, it's cold in your house, you open the door, heat flows in, positive heat flow. It's cold outside, house is all nice and toasty warm, open the door, heat flows out, negative heat flow. So now we can consider the surroundings as the rest of the universe, but that's not always very useful. So oftentimes we're just going to consider surroundings, the area closest to the system. We're not going to look at every little tiddly bit out there, but I could probably just say the heat in the area around my house. And that I don't have to look at, well, I opened the door, how did the temperature change in the United States of America? How did the temperature change on the planet Earth? No, I can look at how does the temperature change mostly around my house, and just look at that, and that will manage for our heat. Now, here's, we got to watch out very carefully when we consider system and surroundings in order to fully comprehend and understand some of these things. So depending on how you set up the systems and surroundings, things can get a little crazy. So we have example A and example B. Example A, we have a beaker, we have a Bunsen burner with a propane tank, and we're heating up the beaker. System B, we have an electrical generator with a resistor submerged in the beaker and a mass that will fall down, thus turning the electrical generator, thus generating current, where the resistor will produce electricity and heat up, thus heating up the water. Now, in both A and B, the system will be the liquid, but the surroundings is kind of important. So surroundings here, we're going to have a diathermal rigid wall beaker, so that means heat can transfer through the beaker. Case A, the propane tank and the Bunsen burner are all part of the surroundings. In case B, the mass, the electrical generator, and even the heating coil are going to be our surroundings. These are perfectly isolated systems, so the total internal energy change should be 0. But in both cases A and B, the liquid temperature will increase and no work will be done with the liquid. The liquid is not going to expand, it's not going to contract. So the internal energy of the system will go up because temperature will go up. In case A, the temperature of surroundings will also increase because combustion of propane will heat up the surroundings as well, the air that's going to surround the beaker. But then why is the internal energy of the surroundings negative if we're also seeing a positive heat? And this is due to we have potential energy loss, that when we break down the covalent bonds in the propane, it's going to be converted into the heat that's going to go. We're going to see some heat gained by the surroundings, but a lot of heat lost as it's being converted and transferred into the system. In case B, we'll see the temperature of the filament increase due to the electrical work, but no work will actually enter the system. The liquid does not expand or compress. No current will actually pass through the liquid. The filament is in the surroundings only. But so how is the internal energy of the surroundings negative, since there's no work being transferred from system to surroundings? And that's because we're losing, once again, the potential energy. And not in bonds now, but now as the mass moves down, it's this gravity, this work of the mass going down is turning the generator, which generates the work in the surroundings. There's loss of potential energy is being transferred into heat. Thus, the work of the surroundings transferred into the heat that is given off. So, right, there's a little thinker. We got to kind of consider these things while we work through this. So one last major concept we'll hit right now is heat capacity. Last example, the electrical work in the surroundings was transferred into heat in the system, resulting in a change in temperature. So one thing we need to think about is heat capacity. And this is a material-dependent property that essentially relates how does the temperature change with a changing heat flow. So now I'm going to have this weird looking D in front of the Q because this is saying we're having a change in the heat flow, but Q cannot be measured, it's already a change, so we can't see an exact differential. But so we're looking at how heat flow will change with changing temperature. So heat capacity is often given as the term C. C, where, as in the things, Q equals MCAT, which is an equation we'll use very often. C is in terms of joules per Kelvin, but we can also turn this from an extensive property into an intensive property as a molar heat capacity. Whenever we see a subscript M below, beside a constant or variable, it's referring to the molar version of that. So we've taken whatever unit we have and divided by the moles. So now this is a constant joules per Kelvin based on how many moles of product. If we have more moles, it's going to take more energy. We're going to get more energy out. If we have less moles, we're going to have less energy because we have to multiply the moles by our C. So in general chemistry, we treated this as an unchanging number. C was constant. But in truth, as we're going to get on in the chapters, C will change a lot depending on the conditions such as state, such as like pressure, such as the initial temperature. So a lot of things will cause this heat capacity to change, and you'll have to deal with that. But the common forms of this is heat capacity at a constant pressure and heat capacity at a constant volume. So already those two numbers are different. So most often than not, liquids and gases, the heat capacity will remain constant. It won't really change. But for solids, heat capacity will vary wildly as a function of temperature. So we'll talk about that in just wait. So what's going on? Why is this mostly constant? So this has to do with molecular motion. Heat absorbed by the atoms will raise the temperature, but heat has a side effect in that it affects the kinetic energy of the particles. So remember, we looked at Boltzmann's constant times temperature is kinetic energy, but kinetic energy is also mass times the velocity squared. So we have some side effects here, is that as temperature goes up, we have some motion. Now, every molecule has three types of motions: translational, which is movement; rotational, which is spinning along the bonds; and vibrational, which is stretching and bending along these bonds. But all of these guys will require energy to occur. If there's zero energy, there's no motion. Now, solids are essentially locked in place. They have a crystal structure. Atoms can't really move too much, especially at low temperatures. So they only have access to some very high energy vibrational movements. Low T, they will not move. So they're locked in place. They could vibrate, but it takes a lot of energy to vibrate. Low temperature, it doesn't take very much heat to change the energy in that system because there's nothing distracting from the efficiency. It's all temperature change goes into heat. But as temperature increases, suddenly we get these side effects of we can suddenly actively vibrate. And so some of the energy goes into these vibrations and suddenly heat capacity jumps up. So it's to increase as we lose some of the heat to these vibrations. So more heat energy is needed to have the same change in temperature of a solid. Now, when we hit the liquid phase, we essentially break up the crystal structure and we get a large degree of freedom with many more low energy vibrations. So because they're allowed to move a lot more, we get a lot of these low efficiency movements that essentially drain the heat energy. So we have a large amount of heat capacity needed to change a liquid's temperature. But of course, once we get to a gas phase, a lot of these vibrations go away because they're exchanged for a lot of translational motion that cannot be used and fully utilized in the solid and the liquid phase. So, and these translations do not consume much energy. So our heat capacity drops down. So it will slowly increase again as we achieve these other high energy vibrations again. But you see, so starts low and goes high, and then jumps up super high for liquids and drops back down lowish again for gases, but with a gradual increase. So we'll look at heat capacity, heat in relationship CP to CV. So we got to prove what heat capacity, what heat at a constant pressure is defined as heat capacity at a constant pressure times the integral of temperature, the change in temperature for that system. Now, remember that heat of a system, heat change of system is equal to negative heat change of the surroundings. So we can look at the QP is delta TF minus delta TI of the system times CP. And that's equal to negative delta TF minus delta TI of the surroundings times CP. So the heat of a system at a constant pressure is equal to the integral. Yeah, we just said that. Now the temperature change in both these do not have to be the same, but the heat flow will. So a lot of heat can fall out of my house without really changing the temperature of the air around my house because there's a lot more air outside. But we can do the exact same thing with the heat capacity at a constant volume, but how do these guys actually relate to each other? So to look at this, we have to imagine two situations. The heat flow of the system result in the same internal energy change. One at a constant pressure, one at a constant volume. So, right here, if the internal energy change is the same, I'll just do it here. Doing it live. The internal energy is the same. Internal energy is equal to work times heat, work plus heat. At a constant volume, there is no work done. No work done. So under this situation, delta U is equal to, let's say, C sub V delta T. But this situation, we have C sub P delta T, how much heat flow is into here. But we also have work, where that's also negative P delta V, which work is done for that situation, plus C sub P delta T. Well, here's that little handy thing. We don't know the pressure, we don't know the volume, but we do know we can relate PV equals nRT. So we can say that delta U is equal to, I'm moving this up here, negative NR delta T plus C sub P delta T, and we're saying that's equal to C sub V delta T. With that in mind, getting the C's on the same side, we say C sub P minus C sub V equals nR delta T. Dividing both sides by delta T, we get this equation. Delta T drops out. C sub P minus C sub V equals nR. So the heat capacity at a constant pressure is greater than the heat capacity at a constant volume based on the number of moles times the gas constant, R, oftentimes 8.314 joules per mole Kelvin. If you turn this into molar heat capacities, N drops out, and it's just C sub Pm minus C sub V, M equals R. And so that's a magic relationship that will come up again and again. So with that in mind, how much heat is required to increase the temperature of 3 moles of carbon dioxide from 30 degrees to 54 degrees at a constant pressure? So just really easy. Okay. I'm gonna jump backwards accidentally. 37.1 joules per mole Kelvin times 3 moles times the delta T. Now I could turn this into Kelvin, but I should, but the difference will be the same. 54 minus 30 is going to be 24 degrees Kelvin. So how much energy? 7.1 times 3 times 24. It has absorbed 2,671 joules, or 2.67 kilojoules of heat. It has to absorb that much. This is why the sign matters. Absorbing energy. Okay, we're going to stop that, and that is where we're going to end for